بسم الله الرحمن الرحيم. رح ناخذ اليوم محاضرة، وهي محاضرة أعتقد إنها رقم 8. تتكلم عن نوعية معينة من الأنظمة، من السيستمز. النوعية هاي أو النوع هذا اسمه Linear Time-Invariant System. Linear Time-Invariant Systems، واختصارا عادة بنسميها LTI Systems. طبعا هذه الخاصية رح نشوف في لها فائدة في التعامل مع هذا النوع من الأنظمة. طبعا قبل ما نبدأ في Linear Time-Invariant System خليني بس أدخل إلى بعض الكونسبتس المهمة اللي قلنا، اللي هم خلينا نحكيهم، اللي هم الامبلس and step responses. شو الامبلس ريسبونس؟ شو هو الستيب ريسبونس؟ اوكي، assume that we have a system عبارة عن transformation. اوكي، you apply an input x of n. Supposedly you are to get an output y of n, which is equal to the transformation of x of n. Okay, this is any system. Now, for exactly the same system, if you apply instead of x of n, delta of n. So your x of n is equal to delta of n. Your y of n, if you apply a delta to the input, then y of n has a special name. We call it the impulse response, and we denote it by h of n, which is equal to the transformation of delta of n. وهذا has a special name. We call it the impulse response. So the impulse response, by definition, h of n, هو the impulse response it is the output of the system, or in other words, the response of the system when the input is a delta. Okay. When the input is a delta, the output y has a special name. We call it the impulse response, h of n. So h of n, the impulse response, it is the response of the system when the input is a delta. Okay, in the same analogy, we can say that if we apply x of n to be equal to mu of n, the step input, then y of n, in this case, so if you apply this to the system, so you will get a special name for the output. It's called S of n, the step response, which is equal to the transformation of mu of n. And in this case, we call it the step response. So the step response, S of n, which we call it the step response, it is the response of the system when the input is a step or a unit step. Okay, is a unit step. Okay, so those are two concepts, two new concepts, the impulse response and the step response. Let me take a simple example and see what will happen here. Consider a linear time-invariant discrete time system with an input output relation y of n is equal to alpha 1 x of n plus alpha 2 x of n minus 1 plus alpha 3 x of n minus 2 plus alpha 4 x of n minus 3. So we have a system, and it's actually weighted sum of x's and previous x's as shown here, and we need to find h of n, which is the impulse response of the system. Okay. So the output when the input is a delta is h of n. So our h of n should be, instead of y, is equal to alpha 1 delta of n plus alpha 2 delta of n minus 1 plus alpha 3 delta of n minus 2 plus alpha 4 delta of n minus 4. And you can see that this sequence, which is called h of n, has a delta at 0 with an amplitude of alpha 1, a delta at 1 with an amplitude of alpha 2. So we can say that my h of n graphically, starting from 0 with an alpha 1 with the amplitude of alpha 1, alpha 2, 0, 1, whatever the values are, I'm just putting the values, alpha 3 and alpha 4, 1, 2, 3, 0, 1, 2, and 3. So alpha 1, alpha 2, alpha 3, alpha 4, at 0, at 1, at 2, and sorry, this one is alpha 3, n minus 3. I'm sorry about that. So this is our example. In different way, we can see that h of n is also equals to alpha 1, alpha 2, alpha 3, alpha 4, and you have the 0 here. So this is my h of n, or the impulse response for such a system. Okay. And by the way, when we have an impulse response in this manner, which has finite values, we say that this system is FIR. So this one is called FIR system. And FIR, this one here, means finite impulse response system. So this system is finite impulse response. Those are the only finite values. The others are all zeros. Okay? Finite impulse response. Which means that the response will, be active for a while and then it will disappear. Okay. Let me take another example. Take an example in a different way. Example 2. So consider an LTI system, linear time invariant system, with an input output relation y of n equals to x of n plus 1/2 y of n minus 1. So this is an input-output relation with the output as a function of the present input and the previous output, combination of those two. Okay, find h of n. So we need to find h of n. To find h of n, we have to substitute the x of n to be, find h of n given that y of n is equal to 0 for n less than 0. Okay, we don't have any y of n for the negative indices. Okay, now we need to find h of n. So h of n will be equal to y of n when x of n is a delta. So this will be a delta of n plus 1/2 y of n minus 1. Okay, now let's substitute the indices. For n equals 0, so you have h of 0 equals to delta of 0 plus 1/2 y of minus 1, which is 0 minus 1, it's minus 1. So delta of 0 is equal to 1 plus 1/2 y of negative indices is equal to 0, so this one is 0. So h of 0 is equal to 1. For n equals 1, then h of 1 is equal to delta of 1 plus 1/2 y of the previous y of 0. So it's 0, 1 minus 1, y of 0. So this is equals to 0 plus 1/2 times 1, which is equal to 1. For n equals 2, you have h of 2 equals to delta of 2 plus 1/2 y of 1. This is equal to 0 plus 1/2 times 1/2, and this is equals to 1/4. If we keep doing this, let me just do it for one more step and make a conclusion. So for n equals 3, then h of 3 is equal to delta of 3 plus 1/2 h of, sorry, no, I have to put here h. I think I have to fix those up and do it in the same way. So y is h actually. So this one is also h. So h of n equals delta of n plus 1/2 y of n minus 1, but because we are applying a delta, then this one is also h of n minus 1. So let's please fix it up here. And this one here will be delta of 3 plus h of 2. So this is equals to 0 plus 1/2 times h of 2, which is 1/4, and this is equals 1/8. Actually, look at those. This is equals to 1/2 to the power 0. This one here is 1/2 to the power 1. And this one here is 1/2 to the power 2. And this one, 1/8, which is 1/2 to the power 3. So we can conclude that the index here is the same as the power here. And we can conclude that our h of n is equal to 1/2 to the power n for n greater than or equal 0. And we have y of n equals 0 for n less than 0. So we can combine those two together. Okay, combine those two statements. We can combine them by h of n equals 0 for n less than 0, 1/2 to the power n for n greater than or equal 0. And this can be done in one statement using the unity step. And we can say that this is 1/2 to the power n mu of n. Okay? 1/2 to the power n mu of n. And you can see here that this h of n will continue until infinity. Although it is decreasing, it's 1/2 to the power n, and 1/2 to the power n is decreasing at the end. But it has an infinite impulse response. So this system is called IIR system. So such a system is called IIR, which is infinite impulse response system. Infinite impulse response system. Okay? All right. Okay. Now, we come to this subtitle, which is talking about the time domain characterization of LTI discrete time systems. Okay. Recall that we could do the following. Any arbitrary discrete time signal can be represented as a weighted sum of shifted deltas. We can say that any x of n is summation from minus infinity to infinity, the weight, which is x of k times shifted delta x delta of n minus k. We showed this to you before. Please go back to the representation of any arbitrary signal and you can see how we derive this equation. So this equation has been shown previously. Go to the general representation or the arbitrary representation of any the representation of any arbitrary discrete time signal, and you can see how we got this equation. Okay, now, so any x of n can be represented as a weighted sum of deltas. Those are the values, the weights of the stems, and the delta is the location where the stem is. Okay. Now, going back to the system that we have, and we say that we have x of n applied to a transformation, and we got y of n. So this is a general representation of a system. Now, let's plug in x of n and see what will happen. Okay. I'm gonna say that my y of n is equal to the transformation of x of n, which is equal to the transformation of the summation from k equals minus infinity to infinity, x of k times delta of n minus k. Notice here that x of k are values, they are discrete values, numbers. Deltas are the sequences. The deltas is the elementary sequence, and this is a summation of some elementary, weighted sum of elementary sequences, which is the deltas. Okay. Now, if the system is linear, then what will happen? This transformation will go inside the summation, and we will end up with y of n to be equal the summation of x of k, because those are constant values. This is the sequence, the function of n, and this is the transformation of delta of n minus k. So this will happen if we have a linear system. The transformation goes inside, weighted sum of deltas, y of n. If the system is linear, then the responses of those, the individual deltas, and we got the output. So this is from minus infinity to infinity. So because of linearity, this goes inside the summation, okay? And you will have the transformation of each delta inside. Now, we know that, as we discussed just a while ago, that the transformation of a delta of n has a special name, which is h of n. Now, if you have a transformation of a delta of n minus k, okay, then this is supposed to be summation from k equals minus infinity to infinity, x of k, delta of n and k. We don't know what is the relation for n and k at the time being. Okay? It's a delta of n and k. It's a function of both. Okay? Okay. Let's add one more property. So the system is linear. Now I'm going to add, beside linearity, to be a shift invariant or a time invariant. If the system is also added to the linearity, we have another property that the system satisfies, which is if the system is also time invariant. So it is linear and time invariant at the same time, then a shifted delta will have a shifted output for, this is for shift or time invariant, let's say, for time invariant or shift invariant, it's the same. So y of n will be equal to summation from k equals minus infinity to infinity, x of k times h of n minus k. This is our final result. And this is called convolution. This is the convolution sum. So if you need to find an output of a system, given that you know the impulse response of the system, all you have to do is to convolve the input with the impulse response, and you can get the output. Okay? And this is very important result in the time domain representation of the signals and systems. So let's rewrite this equation again. Y of n is equal to the summation from k equals minus infinity to infinity, x of k times h of n minus k. And we said that this one is the convolution sum. And actually we can have it as symbolically, it's x of n star with the circle h of n. So this star with the circle means you are performing the convolution sum over x and h at the same time. Okay, by the way, this formula is also commutative. So you can say that this one, y of n, is also equal to summation from k equals minus infinity to infinity, h of k times x of n minus k. It's also the same, it's the convolution sum. And y of n is equal to h of n star circled x of n, which is equal to x of n star circle h of n. So this is commutative operation. يعني هي عبارة عن عملية تبديلية. You can fix h, fold and shift x. Sorry, you can fix h, fold and shift x, or you can fix x, fold and shift h. So either or, both are okay. How can we move from here to here? Just rename the variables, let this n minus k equals m, and then find m in terms of k, substitute the variables, and you end up with the solution. It's very easy to show it. Okay. What does that mean? Convolution sum. It means that if you are given x of n and h of n, or let me just put it in another way. If we are given h of n for a system, we can find y of n for any input x of n by performing the convolution sum. It means that if you have h of n, you apply x of n, and you get y of n to be equal to x of n convolve star with h of n. Okay. Let's take an example and see how we are going to perform this. Notice that in the summation, y of n is equal to summation from k equals minus infinity to infinity, x of k, h of n minus k. So the process of doing this summation is Let x of k as it is. X of n is the same as x of k. Just rename the indices. Rename the index. H of n minus k, it's flipping the values of h of minus k, and then shift it and do this for n going from minus infinity to infinity. Okay, let's do this with an example. I'm going to take the following example. We have x of n is equal to minus 2, 0, 1, minus 1, and 3. So when we have the 0 here, even if I don't put the arrow, you have to take care that, to be careful that if you don't put any arrow inside, then this is the default value of the arrow. So the n equals 0 is the first element. Okay, and h of n is equal to 1, 2, 0, minus 1. Okay, so this one is 1, 2, 3, 4, 5. It's length 5. Length 5 signal or sequence. And this one is length 1, 2, 3, 4, length 4 sequence. Okay, so you have a length 5 sequence, and this one is length 4 sequence. And we need to find y of n, which is equal to x of n convolve with h of n. We need to do the convolution sum for those two. Okay, to do this, I'm going to perform this in more than one way. The first way that I will do it is I will do the summation exactly. I'm going to go with the mathematical solution. So y of n is equal to summation from k equals minus infinity to infinity, x of k, h of n minus k. Okay? Now, y of n is equal to summation. Now, my x of k here, x of k, I'm going to change the index n to k. So you have k 0, 1, 2, 3, 4. So I'm going to have only non-zero values from 0 up to 4. So this is from k equals 0 to 4. X of k, h of n minus k. Okay? Why did I substitute k equals 0 to 4? Because this x here, starting from 0, 1, 2, 3, and 4. So x of k. Otherwise, the items are multiplied by x of k with k outside this region, and x of k is equal to 0 outside this region. Okay? So this is my formula, my initial formula. So this is how we start. We look at x, where x has non-zero values, and we put the index that decided x of k with non-zero values. Okay, now I'm going to start substituting values. Y of 0, and I'm going to put here 0. So for y of 0, this is equals to summation from k equals 0 to 4, x of k, h of minus k. So you put 0 minus k, and you end up with this summation. Now let's substitute the values. So you have x of 0 times h of minus 0, which is h of 0, plus x of 1, h of minus 1. Plus x of 2, h of minus 2, 0, 1, 2, 3, 4. plus x of 3 h of minus 3 plus x of 4 h of minus 4. Okay, looking at h starts from here, so you have 0, 1, 2, 3. All those negative h's has 0 values. So this one is 0, this one here is 0, this one here is 0, and this one here is also 0. So the only non-zero value is h of 0 times x of 0 times h of 0, which is equal to x of 0 is minus 2 times 1 minus 2 times 1, which is equal to minus 2. Okay, minus 2. All right. Okay. Let's move to the next one, y of 1. So n is equal to 1. This summation from k equals 0 up to 4. 5 values, x of k, h of 1 minus k. H of 1 minus k. Y of 1, so n is equal to 1. So this is equals to x of 0, h of 1 plus x of 1, h of 1 minus 1 is 0 plus x of 2, h of 1, minus 1 plus x of 3, h of minus 2 plus x of 4, h of minus 3. Negatives are all zeros. All h's are positive indices. X of 0 is equal to minus 2 times h of 1, which is equal to 2, plus x of 1, which is 0, times h of 0, which is 1. And the answer is equal to h of 1. Yeah? Y of 1 is equal to minus 4. Okay. Y of 2. Y of 2 is equal to summation x of k from k equals 0 up to 4, h of 2 minus k, and this is also equals to x of 0, h of 2 plus x of 1, h of 1 plus x of 2, h of 0 plus x of 3, h of minus 1 plus x of 4, h of minus 2. Those two are zeros. And you have x of 0, which is equal to minus 2, h of 2 is equal to 0, plus x of 1 is equal to 0 times 2, plus the third one is x of 2, 0, 1, 2, it's 1, times h of 0, which is 1, and we end up with y of 2 is equal to 1. Okay, I'm gonna let the others as a practice. Please do the other values. Where will be the last value? The last value will be when y of n equals, or for n equals 7. Y of 7, when you have y of 7, then this is equals to summation from k equals 0 up to 4, and this is x of k h of 7 minus k. Okay? And this is equals to x of 0 h of 7 plus x of 1 h of 6 plus x of 2 h of 5 plus x of 3 h of 0, 7, 6, 5, 4 plus x of 4 times h of 3. Notice that here, the index here is 0, 1, 2, and 3. This is the last index, which is the last index here. So h of, all those h's are zeros. Except this item here, which is equal to x of 4, 0, 1, 2, 3, 4, the last one, which is 3, times the last item, h of 3, which is minus 1, and the answer will be minus 3. Minus 3. So just, I gave you the last item that we will have, which is the last item here. If you go beyond 7, then you will have zeros multiplied by zeros, and the end result is a 0. Okay, I'm going to put the final answer so that you can make sure that you get exactly the same answer. My y of n, so my y of n is equal to minus 2, minus 4, 1, 3, 1, 5, 1, and minus 3. And we have the 0 here. Okay? So this is our solution. Notice first that when you have 5 elements here, 4 elements, then the sum of n1 plus n2 minus 1 is equal to m, which is the length of this sequence. So m is the length, y of n is length m sequence, where m is equal to this formula. The length of the first x of n plus the length of h of n minus 1 is equal to the length. Okay. One more item, I will talk about it in a while. We can do this graphically also. So we can do the convolution graphically as we did in signals and systems. So if I take the first signal and I'm going to rename, so I'm going to call this graphical solution. I'm going to take the first signal and rename the index to be k, and x of k will start from 0. This is minus 2, I'm sorry, it's going down. So minus 2, 0, 0, 1, 2, 3, 4, 5. Okay, at 2 you have 1, 0, 1. Okay, so this is our 0, and until 4, 5 elements, 1, 0, -1, and 3. So this is our signal, x of k. Now, to do the convolution in time domain, we're going to take this one and flip it. So once we flip it here, we will have a sequence that will start at 0. Now we flip it around the 0 axis. So this one will be like this. So 0, -1, -2, and -3. So the one at 0 is the same as 1. -1, you have 2 at -1, and you have a 0, and you have a -1, -2, and -3, and this one is -1. So this is this one here is x of k, and this one here is h of -k. Okay, h of -k, if we go down by 1, so you have -1 k, you don't have any overlap between the indices. So I'm gonna do the summation. Y of n equals to the summation x of k times h of n minus k from k equals 0 until 4. Now, or we can say that, okay, this is from -infinity to infinity. Doesn't matter. Okay, now if I'm taking n equal to 0, then h of 0 minus k, this is h of minus k. And this is the first element that we will get. So for n equals 0, y of 0 is equal to the summation from k equals -infinity to infinity, x of k, h of minus k. If we look at this, this is the multiplication, x of k times h of minus k, and do the summation. The only sum, non-zero sum, is the multiplication of this. So y of 0 is equal to the only -2 times 1, which is equal to -2. Now, if I need to find y of 1, so I'm gonna have here 1. So this one should be h of 1 minus k. Y of 1 is equal to x of k times h of 1 minus k. H of 1 minus k should be a signal that is shifted by 1 to the right. So you will have 1 here, you will have 2 here, you will have a 0, and you will have a -1 at -2. Okay, so we shift this one here, and this one is h of 1 minus k. H of 1 minus k. So this one will be multiplied by this one, and we'll do the summation. This one multiplied by this one multiplied by this one, and you end up with y of n is equal to 2 times -2, or -2 times 2, which is equal to -4. Okay? Y of 2, then we have to shift this signal by 2. So h of 2 minus k. So we'll go by the signal 1, 2, and 0, and -1. Multiplication 0, 1, 2. Multiplication of this one times this one, plus this one times this one, plus the third one. So you will have 1 times 1 plus 0 times 2 plus 0 times -2. 0 times -2, yeah, plus, and you end up with 1. Okay, and we continue shifting h of 3 minus k, h of 4 minus k, until we reach h of 7 minus k, And h of 8 minus k, the whole signal will be outside, no multiplication, no overlapping between x and h, and the end result will be this sequence here. But we will do this graphically. Please, as a practice, do the rest of the graphical solution. Okay? Yeah, as you can see, this is a tedious problem, tedious job. You know, it's really exhausting, lengthy, and it takes a while to do it. Let's do it in a different way. We will teach you how to do it in a very easy manner. Okay? We'll call something the tabular method for convolution sum. Okay? So we'll use a table. What we will do here, we'll make a table. This is our index n, 0, 1, 2, 3, 4, 5, 6. And we will arrange x of n underneath -2, 0, 1, -1, and 3. And below x of n, we will also put h of n as 1, 2, 0, -1. So those are the two sequences, and this is the index n that we have. Okay, here, and we put 7 here. It's an 8 element, yeah? Okay. We'll do the multiplication as we do in our real life multiplication. I'm gonna take the first element, multiply it by x of n. So I'm gonna take the 1 here, multiply it by -2, 1 times 0, 1 times 1, 1 times -1, and 1 times 3. So 1 times the whole sequence. Now, in the next step, I'm gonna take 1 digit. I will leave 1 digit and start from below 2. 2 times -2, it's -4. 2 times 0, 0. 2 times 1, 2, sorry. 2 times -1, -2. And 2 times 3 is 6. Okay? So 2 minus 4, 0, 2, -2, and 2 times 3 is equal to 6. Then we'll take 2 digits here, and we will leave 2 digits, okay, 2 spaces, and do the 0. So the 0 will be all zeros like this. And the last one is -1. We'll take 3 spaces and go underneath the -1 here. -1 times -2, it's 2. -1 times 0, 0. -1 times 1, -1. -1 times -1, it's +1. -1 times 3, it's -3. We don't have any more data, so we will stop and we will add. So this is -2, -4, 1, 5, yeah, the last one, yeah. Sorry, -1 times -2, it's 2, yeah. So 2 plus 2, 4 minus 1, it's 3. Okay, 1, 6, 5, 1, and -3. Yeah, and this is my y of n. So by the tabular method, it's a very simple, very straightforward. You don't have to do it step by step. You do it in a table, multiplication in a very simple manner. Take the spaces, add. And where is my 0 index here? Because this one is at 0, this one is at 0, so mine will be at 0. Okay? One last thing to explain here. What if what if the indices were not in the first place, not in the first item? I mean, I'm gonna show you if let me put it as an example. If x of n is the same as -2, 0, 1, -1, and 3, and h of n is equal to the same as this one, 1, 2, 0, and -1. See, if we let that, or assume that we have the 0 here for this one, and you have the 0 here for h of n, okay? So this is -1 index, sorry, -2 index, -1, 0, and 1 and 2. -1 index, 0, 1, and 2, okay? What will happen? We can use the summation method, which is the mathematical method. We can use the graphical method, and we can use the tabular method. Okay, all of them applies. How can we implement the tabular method? What we will do, we will replace the arrow. So if the arrow is underneath the 1, I'm gonna take the arrow and put a decimal point here. So I'm gonna put the decimal point beside the 1, where we have the arrow underneath. And we will put also a decimal point here. And we will do the same procedure, the same way that we used to do multiplication when we have decimal points in our real life. And we multiply, then we add how many digits after the decimal point. We will do this with the resultant. So in our answer for this, to have it here, the same tabular method will apply. Just replace the arrows with the decimal point, multiply, then count how many digits after the decimal point. So you have 1, 2, 3, 4. So 1, 2, 3, 4. And you have to have a decimal point here, but we will replace it with an arrow. So this is our resultant. You will have y of n is equal to this, and this is your n equals 0. So if you have those two sequences, then your y of n as an answer will be exactly the same answer, but it is shifted. -2, -4, 1, 3, 1, 5, 1, -3. And the arrow will be underneath the 3. So one more remark here. So the first remark that we did is that if you have a sequence with 1, 2, 3, 4, 5 elements, and 1, 2, 3, 4 elements, 4 and 5, 8, 9, -1, you end up with 8 elements. 1, 2, 3, 4, 5, 6, 7, 8. So you have an 8 elements. If your index here, the first very index of your sequence, n equals -2, and here is n equals -1, so your very first sequence here, your n is equal to -1, -2 equals -3. So 0, -1, -2, -3, which is the addition of the first sequence, the first index in H plus the first index in X. Their summation is -1, -2 is equal to -3. So y of n is the content, or let me say that the length and the starting index of the sequence y of n is decided from x of n and h of n themselves. How many items here, their summation -1 is the number of items in y of n. Where the index should start, it's the first very index in x plus the first very index in h, and their summation is the first very index of y. Okay, with this we come up to end our lecture. I hope you will find it very interesting, and we'll see you in next lecture. Thank you very much.